So let's move on to something more interesting, which is this counter class. And before we even look at the definition, let me show you how it works. So define C2 instantiate counter. And there are no instantiation variables. That's all I have to say. And while I'm at it, I'm going to make another one. I'll be quiet. Not interested. Thank you. Okay. So now I can ask C2 next. I'm going to, and now I'm going to do that again, and again, and again. Okay, so every time I say next, it gives me a different answer. So this shows that we're not doing functional programming, right? I call the same procedure with the same arguments, and I get a different answer each time. So we're out of the realm of functional programming, which clearly is, and into the realm of local state. Local means that each object has its own memory. So I can ask C3, quote, next, and it starts from 1. And now I can go back to C2, and it still remembers that it was at 4, so it gives me 5. So each counter has its own separate count. That's what local state means. Okay, questions about the idea? Yeah. Okay, the question was, I can predict what C2 is going to do next. It's going to say 6. So why is it not functional? Again, the definition of functional programming is that every time you call the same procedure with the same arguments, you get the same answer. Right? There can't be any memory of past history. And what that buys you, again, is the absolute certainty that that other piece of the program isn't going to do anything that affects this piece of the program. So for example, if you want to have multi-core computers doing things in parallel, you can, let's say you're looking at a function call with 3 arguments, each of which is itself a function call. Okay? So we can take those 3 function calls and give them to 3 different processors, and we don't have to worry at all about who finishes first or any of that stuff, because they aren't interacting with each other. Whereas if we have a function call and 2 of the argument expressions are both ask C2 quote next, then we have to worry about, okay, is this one going to be 6 and that one 7, or is this one going to be 7 and that one 6? Okay? So that's why it's not functional. Other questions? Yeah. Yeah, okay, so now let's look at the way it's actually defined, which is up here. And the thing that's new is instance vars. And the way to think about instance vars is it looks kind of like a let with name-value pairs. Okay? Well, the first part of a let. It doesn't have a body. So let me write instance vars up here on the board. And I'm going to write instance variable over here. In our vocabulary list. And notice that the name instance variable is a lot like the name instantiation variable. And the ideas are very much the same also. The difference is, where does this variable get its initial value? Okay, when we create an instance, how do we know what the value of real part is, or how do we know what the value of count is? For instantiation variables, the values come from the call to instantiate. So back here, when I made the complex number C1, that's when I said what the value of real part and imaginary part should be. Okay? Whereas for the instance variable, when I instantiate counter down here, I don't say what the initial value of count is, because every instance is going to start with the same value of count, and so I put it here in the definition of the class. Okay, does that answer your question? Okay, so initial value from the class definition, that's an instance variable. Initial value from the call to instantiate, that's an instantiation variable. And the purpose of the difference is, does every instance have the same starting value, in which case we use an instance var, or does every instance have a different starting value, in which case we use an instantiation variable? Okay? So that's one big difference here. The next big difference is this. That's an exclamation point right there. It's pronounced bang. So this is set bang. That should go on another list. Set bang is an official, built into scheme, special form. That its notation is just like a define, the kind of define that doesn't imply an invisible lambda. So you say define name value. We say set bang name value. The difference is define creates a new variable. Set bang, the variable has to already exist. So if there weren't an instance var's count in here, then it would be an error for me to say set bang count to whatever. Right? This is what makes our objects non-functional, is the ability to change something that already exists. It's different from let. Right? Let kind of serves the purpose of give this variable this value. And you may have been thinking about let in the past when it's part of a recursive procedure as if it were kind of an assignment statement to an existing variable, but it's not. Every time you run a let, it makes a new variable for each of its name value pairs. So if there was already a variable of that name, then they both exist. There are two variables with the same name and different values, and they're both around, and which one you get depends on where you are in your program. Set bang is not like that. It doesn't make a new variable. It changes one that was already there. The convention in scheme, and again, it's not enforced by the language, it's just a convention, is that anything that changes the value of something has an exclamation point in its name, like set bang. To let you know that it's doing mutation, because that's very important. It means you're not doing functional programming. Okay, so if there aren't any exclamation points in your program, then you are doing functional programming, basically, and if there are, then you aren't. So the method next, I mean, it's not very subtle. It says, take the value of count, add 1 to it, and replace the value of count with this new value. In other words, add 1 to count and make it the new value of count. And then, when you do set bang returns the word OK. In the scheme standard, it says the return value is unspecified. We make sure to return something useless to kind of rub in that it's unspecified. And that's why after the set bang, we have this count here. So you've actually seen things like this before with print instructions, but officially this is another new thing that we're giving you, which is up to now, the body of a procedure has pretty much always been one single expression, because a procedure can only return one value. That's still true. A procedure can only return one value. But it's possible to have more than one expression in the body of a procedure. If so, those expressions are evaluated in order. So first we do the set bang, and then we evaluate count. The value that the procedure returns is the value of the last expression. The values of all the earlier expressions are ignored. Okay? They're computed and ignored. So presumably, all but the last expression are in there to have an effect on the world, to do something, rather than to return a value, even though they all do return values. The values might be things like OK. Or the value might be something that would conceivably be useful, but we're just not interested in preserving it. And then the last expression, the value that it returns, is the value that, in this case, your method next returns. Questions about that? Yeah? Can you do set bang of instantiation variables? Yes. Once the variable's there, you can treat it like any other variable. Yeah. Another question? Yeah? Right. Yeah, if you wanted to say what the initial value of the counter was, then you would make count an instantiation variable rather than an instance variable. That's exactly the difference between instantiation variables and instance variables. So our variable, the initial value is 0, but the first value return is 1, because we do this plus count 1 thing before we return the value. Yeah? Can set bang take a procedure as a value argument? Ah, thank you. Good. Remember first day of class, I said over and over again in this class, people are going to say, can I use in the context of? And the answer is always yes. Right? This is one of those. Yes, absolutely. The value of a variable can be any legal scheme value. Okay? It's a hard idea to get through your head that that's always true, but it's a great principle.